Today I will be speaking about what's new in YOLO series of object detectors. So I divided my speech into three parts. During the first part, I will be speaking about the problem of object detection. I will introduce to those of you who have less experience with those models, and then I will be talking about the YOLO series, which is a kind of algorithm for solving object detection tasks. And then in the end, I will be speaking about what's new in this area of research. So when speaking about object detection, I'm sure many of us have, in our daily lives, we're using it, but maybe we're not paying attention much on that. The basic example that comes to my mind is when we're trying to count something by looking at some image. So, for example, I think you have seen this episode from Mr. Bean when he's counting number of sheep in an image, and they say it helps for people to fall asleep quickly. So imagine we want to count number of sheep in the image, and this will be the prime example of for me to explain how these algorithms work. So we have an image, it contains some sheep. I didn't count number of them, but so this is the problem and we're trying to solve it. Object detection models typically divide into two groups, one-stage detectors and two-stage detectors. Two-stage detectors, they're a bit slow because they, as the name says, they consist of two stages. The first stage is when we divide the image into regions where potentially objects can be, and then we're feeding these cropped regions to a classifier model so that it can say what type of object is in that region, etc. But the one-stage detectors, they do this process once, and they generate the predictions, and that's why they're pretty fast. And YOLO series of algorithms, they belong to this type of method. They're one-stage detectors. That's why they're generally very fast. So YOLO is an abbreviation. It's opened as you only look once, meaning you only look once at the image. And when we want to use the model, we typically resize the image. We make it square, and it's already done. And the first step of the algorithm is we're kind of dividing the image into some grid cells. Typically, it's done in multi-scales so that our predictions later can be of different scales, not just one scale. And then when we divide, when we do this division, there are some boxes that are called anchors, which are used to help spot objects in the image. During the training process, each anchor gets one ground truth object. When I say ground truth object, I mean real sheep. So we have annotated data, we have the sheep into bounding boxes, and during the training process, these anchors are used to match the real ground truth boxes, and for all grid cells, this process is being done, and for all the typically three stages of scales. These anchors are represented, like they have associated vectors with them, which are the 4 coordinates of the rectangle, objectness, which basically gives us information about what is the probability that there is an object in the image, and then k number of class conditional probabilities, saying that if there is an object in that rectangle, what is the probability that it is, let's say, sheep or table. And then when we're training these models, the loss consists of 3 parts: objectness, classification, and bounding box regression for the above mentioned values, so that we can make those values to be close to the ground truth labels. And then during the inference process, when we feed the image to the network, we're getting predictions. The predictions are the anchors, basically, for all the grid cells and for all the scales. And each anchor has a score, a confidence score, which is calculated by multiplying the objectness to the class conditional probabilities so that we can get the probability of having a particular object, let's say sheep, in that cell. And then we're taking the maximum, and it becomes the score of a particular anchor. Then we're sorting these anchors in descending order so that the higher scores are first, and then we typically have a predefined threshold for the confidence. Let's say we only want to see the predictions that are higher 0.5 probability. And then there is another step involved when we're filtering occlusions, because there may be multiple anchors pointing to the same object. We don't want this to happen. That's why we typically have a filtering stage involved. Okay, so we basically have an idea how these methods work, and now it's time to see what happened from the beginning of the YOLO series. So they started in 2015, the first version, and we will be looking at them from the different perspectives. Let's say some of the methods initially didn't have anchors. For example, the first version was anchor-free, but later they started adding it. They didn't train the methods by feeding to the model images of different sizes during the first version, but then they started doing that. It helps the model to learn more fine-grained features from different scales. Starting from third version, they added type of feature integration, feature pyramid networks, which is the idea of making predictions of different scales. But then starting from the fourth version, they changed it. They modified it, and they added partial aggregation networks, which adds more shortcut connections, and which basically helps during the prediction phase to have more good features from the lower levels of the encoder, the backbone. Then, starting from the fourth version of YOLO, they added a receptive field enhancement block, which is called spatial pyramid pooling, which basically helps the model to locate bigger images, bigger sized objects in the image. And it has different modifications. For example, in fifth version, they add a faster version of this spatial pyramid pooling. And then in scaled YOLOV4, they CSPize this block. And later I will explain what CSPization is. They started using strong data augmentation from YOLOV4. Before that, they only changed the colors, resized the image. But starting from V4, they used mosaic data augmentation, where they concatenate 4 images or 9 images and feed this image to the model. They also use copy-paste, cut mix, and different other methods that help the training process. CSPization was introduced starting from the fourth version. During that, only the backbone had those kind of blocks, but then during the scaled YOLOV4, pretty much all the blocks had this feature. And as I said, I will touch that feature later on. And starting from YOLOV4, they used IOU intersection over union based loss function for bounding box regression, instead of using just L2 loss. And the reason why they did it, because it's not a good idea to treat those bounding box coordinates independent from each other. That's why they started using intersection over union-based loss. Okay, so the main point of YOLOV7 algorithm, which is the newest one, it was released in July, beginning of July this year. And so they use model re-parameterization, which is when we train, for example, when we train multiple models and then we aggregate them. Let's say we take the moving average of the weights, and then during the deployment process, we're using that final checkpoint, which typically helps to gain more quality model. When we're mixing some weights of the model, that's a model-based re-parameterization, but there is also module-level re-parameterization, which is when we have multiple blocks of the same type, and then during the training, we're training all of them, but during the inference, we're, let's say, adding all of them, and then we're having just one of those blocks. Basically, it's train multiple things, but use one of them during during inference. Then they're kind of introducing a new kind of model scaling method when we have a model, but we want to increase the capacity of the model or we want to decrease it. There are many, like this is a huge research direction, and typically there are 3 dimensions that we scale the model. It's the width, the number of channels in each of the convolutional layers, depth, the number of layers that our model consists of, and the input resolution. So we're feeding a bigger sized image or smaller sized image. They have a new layer, a new computational block, which is called Extended Efficient Layer Aggregation Network. And they started using dynamic label assignment, and they introduced a new type of loss, which is called assistant loss for auxiliary head. Okay, let's see what each of these means. Okay, model re-parameterization. So this computational block, which is called rep-conv, was introduced in rep-VGG paper. This is not something that the authors of YOLOV7 came up with. They're using this, but they modified it. They did some ablation study and came up with some conclusion, which I will say shortly. But the basic idea is that during the training process, there are 3 branches. The first branch is the output signal from the layer before that just adds a batch normalization, and then it gets added here. And then this is just a 3x3 kernel convolution following a batch normalization, and 1x1 convolution, again, following with a batch normalization. So during the training process, all of this gets add up, and then an activation function is applied. But during the deployment, all of this, the weights of these separate convolutional layers adds up. We're having one convolutional layer with its bias instead of batch normalization, and then an activation function is applied. And the way we are combining the weights of these independent units is illustrated in this image, which is taken from their paper, and it's I think it's very good illustration, and they also explain it. If there is time, I will go over it if you're interested later. What they did is they did some experiments, and they found out that this computational block does not work well with residual and concatenation-based blocks. Particularly, we should discard the identity connection, basically this part, when we are dealing with residual or concatenation-based models. So this was their conclusion after this study. Model scaling. So as I said, there are 3 dimensions: width, depth, and input resolution. And when we are trying to combine all of these dimensions, we are calling it a compound scaling. So they figured out that in concatenation-based models, when we want to increase the depth of the network, so for example, we have 3 convolutional layers. We want to add 1 more. We're having 4 convolutional layers, but then when we concatenate them, instead of having 3 C, let's say, width at the end, we're having 4 times C width, which means that by changing the depth, we also change the width, let's say unconsciously. That's why they're offering, whenever we apply depth scaling to these concatenation-based models, we also whenever we're applying depth scaling, we also should apply some width scaling so that the outcome does not change. So we apply something so that we have 3 times C number of channels at the end. And by doing this study, they improved the quality of the model by 1%. Yeah. Okay, so the efficient layer aggregation networks, they introduced this extended one, which is based on this block, which I will cover in more detail in the next slide. But what was surprising for me, they did not include the code of this block in their code base. So in their code base, in their models, you can only see this one, which is which was introduced earlier this year, but the author is anonymous, and I couldn't even find the paper. This is that computational block. Remember that I was talking about CSPization. It's opened as cross-stage partial, I think, or partial, or anyway, cross-stage connection. The idea is that whenever we have the output signal from the earlier layer, we divide in 2 branches so that a part of the output signal goes to a simple 1-by-1 convolution and then gets concatenated from the end. This stage helps us to keep the spatial dimensions of the output signals, spatial features, let's say. And then the other layer takes half of the channels and applies some convolutions from the beginning 1-by-1 and then 3-by-3 convolutions, and then concatenates and another convolution. And then we have the output layer. And they also, in their model, they also use another type of this architecture, which they didn't name. I just named it version 2, just to include it in this slide, because they're using this computational block as well in their models. Dynamic label assignment. So earlier on, the models were trained using fixed label assignment, which is the process when I described earlier, when we have anchors and we're trying to assign each anchor with the ground truth target by using intersection over union. But in 2020, there was a paper introduced that used optimal transportation assignment for this anchor assignment process. And the idea is the following. We have m ground truth targets. We have n anchors for each image. Each ground truth target can be assigned to multiple anchors, but each anchor just gets assigned to 1 target. And then we're introducing a cost matrix, which consists of classification and regression losses for each of the let's say anchor candidate and ground truth bounding box. And then we're trying to, this image is more illustrative. We're having the cost matrix, And then we're applying synchron NOP iterations so that we can get the following matrix, assignment matrix, which basically tells us whether the anchor gets assigned to a background or to an actual target. And they also add a background class in the original paper so that they take it into account during the optimization process. But what was surprising for me in the YOLO's paper, they didn't consider using the backgrounds. And yeah, so assistant loss for auxiliary head. In YOLOV7, they introduced auxiliary head. So earlier versions only had 3 heads for multi-scaled predictions, but they also introduced 3 other heads, which are basically used for supporting these final detection heads. How they do it, there are 3 different strategies. Independent assigner, which is, this is the only version that's available in their code base. They use the assigner independently to assign to the auxiliary head and then to the lead head. Then the final loss is computed by multiplying, like taking 0.25 of this and the whole part of it. And their contribution were these 2 methods. The lead guided assigner is the one that we're using the prediction of the lead head to train the auxiliary head, basically. So, and at the end, we're having like this auxiliary head makes predictions which are kind of not complete, and lead head is responsible for completing these predictions. And this version is a bit different. The lead head returns 2 types of predictions. One is like fine predictions, and the other one is coarse. And basically, it adds some more stuff. But at the end, what's more important, I think, the improvement that they got when they introduced these types of auxiliary head, I think my personal opinion is that it's not a significant improvement, but still, this is something they introduce. Okay, finally, this is the YOLOV7 architecture. I couldn't find an image like this on the internet, so I thought maybe it's a good idea to make it. So where should I start? I introduced these computational blocks. I have not introduced this one, but it will be on the next slide. As you can see, the re-parametrized convolutions are here at the very end. And when I was saying predictions of multi-scale predictions, I meant these ones. So we're getting grid size of 80 times 80 for objects that are small, and for bigger objects we're having this layer, which gives us bigger objects basically during the prediction phase. This is the FPN part of the architecture, and this whole thing is the PAN architecture. And later, if you have any questions, I will answer them. What was interesting for me for downsampling the spatial resolution of output maps, they used MaxPooling, but they also used convolutional layers for that with Stride 2. And this architecture is also, I think, inspired from CSPization. And yeah, basically. Okay, coming back to counting sheep, I tried YOLOV7 on this image so that we can see how they perform. So the vanilla, let's say, YOLOV7 found 23 sheep on this image. I checked, there were no false positives. The architecture has 36 million parameters, and I gave 125,024 size of input. I think this was impressive. It was not false positive. And then I tried the biggest architecture of their model, which was actually trained using the auxiliary head, which I introduced. And it could only find 18 sheep in the image. It has 151 million parameters. And then, attention, tiny version of the model. It could find 27 sheep in the image. It doesn't find this one, but we can see this second row could be detected. It has only 12 million parameters. It's hard to tell the reason why this happens, but I mean, I can give some guesses, but if they would do some qualitative experiment in their paper, maybe we could say more. But having a look at just this example, we cannot say much, I think, why this happens. Okay, I think this was it. If you have questions, I'll be happy to answer. Just for information, there is an avenue called YOLO in Berkeley. A friend of mine took the image, so I thought it's a good idea to include it. Yeah, if you have questions.
Thanks, Nshan, for the presentation. Just two small questions. First, like you present only like 5 versions of YOLO, and there are like intermediate, like still 4 or 5.
Yeah.
There are some reasons for not doing that. And second, when you were showing this vanilla case of YOLO, yeah, it's kind of yeah, this. I mean, it feels strange that you can guess this really small scale, but at least like for one of them, and cannot guess the intermediate one. I suppose that logically and intuitively it should be able, yeah, to do that. Any guesses why?
Well, I didn't have time to dive more deep into these results. I could, for example, make the confidence level low and see if these sheep get detected with low confidence. And it would mean that maybe they didn't train for longer iterations. Model is underfitted. But there may be different reasons. For example, the sheep here are occluded. They're very dense. Maybe that's another reason why they couldn't be detected. And maybe the lighting also affects, because I think it's more sunnier, like the light gets on this sheep more than on this one. But again, these are guesses why this couldn't help. And regarding the other question, yeah, there are many types of YOLOs. For example, there is also YOLOV7. But so the reason why I didn't include, for example, that one is that it doesn't have paper, and it's hard to understand what's their novelties. I mean, I could dive into their code base and understand what they did, but I mean, it was time consuming. There's also YOLO-R, which gets mentioned in their paper quite a lot, but it's a bit different. They're trying to solve multitask problem, and then they're just taking the object detection branch, and they're, yeah. And also that, I mean, if I would also include that in my comparison, the time would take too long for me to explain what they did, because they introduced quite new stuff for doing that multitask learning. But if you're interested, I will share you more knowledge about those papers later, because I did some research on that as well.
Another question? Do you know how the more state-of-the-art YOLOs compare to the other state-of-the-art image detection and efficient
I mean, they include that evaluation in their paper. I did have a look, but to be honest, I cannot say.
they're competing in parallel
Yeah, basically they're competing. I can say it's, they say it's quite faster. I think 100 and something times faster than other versions of YOLO. And in terms of the accuracy as well, but I don't remember the numbers. So this is the state of the art, as they say.
I have one question connected to datasets. Did you know the evaluation of dataset? It changed it in connected to YOLO versions 1, 2, 3, or 5, 6?
During the first version of YOLO, I think they used the VOC dataset, VOC. But I think starting from the third or from the second version of YOLO, they started using COCO dataset. Until now, they're basically doing the benchmarks on that dataset, which has 80 classes. But VOC, I think, has only 20 classes of objects.
Other questions? Okay, thank you, Nshan.
Thank you.